Hello guys, welcome back to a new video. In this video we will be finishing the questions that we have left from chapter 4, review and assess. 26. From the heating curve for a 23 gram sample, estimate the following properties of the substance. A, the specific heat capacity of the liquid. So first of all we have mass, which is equal to 23 gram. Let's change that to kilogram. It's going to be 23 times 10 to the power of minus 3 kilogram. This is our mass. We will be using that throughout solving the question. Before that, let me explain this curve that we have, this graph that we have. From the left side, we have temperature, which is measured in Celsius, from 0 Celsius to 600 Celsius. From the bottom, we have heat, which is measured in kilojoules. It means whenever you are using these numbers from 0 to 857, we're going to multiply them by 10 to the power of 3 because you have to change joules to kilojoules to joules. Let's solve the first one. It says the specific heat capacity of the liquid. Remember, whenever it says the specific heat capacity, you have to use delta T. You have to have delta T, T final and T initial. Whenever it says latent heat, temperature should be constant. Okay, now we have the first one. Okay, it says the specific heat capacity of the liquid. Where is the liquid? As you see, this is the liquid. Okay, here is the liquid. From 12 kilojoule to 16.6 kilojoule. Now, if you make a straight line, you will see that T initial is going to be 150 and T final for the liquid is going to be 300. Okay. For heat, which is Q, I'm going to subtract 16 by 12. This is how much heat the liquid has. Now, let's solve A. A is equal to Q, which is equal to Cp mass delta T. I'm going to find the specific heat capacity. So Cp is going to be Q divided by mass times delta T. Cp Q is equal to what? 16.6. Do not forget 10 to the power of 3 times 10 to the power of 3 minus 12 times 10 to the power of 3. Divide this by what? By mass, which was equal to 23 times 10 to the power of minus 3 times delta T is going to be what? It is going to be 300 minus 150. Subtract all of this. Calculate all of this. And Cp of the substance is equal to 1.33 times 10 to the power of 3 joule per kilogram per Celsius. That is A. B, the latent heat of fusion. So remember, latent heat of fusion was what? Was the energy needed per unit mass to change a substance's phase from solid to liquid or liquid to solid. Here, where is the liquid and solid? It is here. You see, I told you when you are dealing with the latent heat of fusion or latent heat of vaporization, temperature is going to be constant. So where do you have solid and liquid both, and the temperature is constant? Here, look, this line is straight. It means that the temperature is constant. I have 1.85 to 12 kilojoules. Now let's find the latent heat of fusion. B, Q is equal to MLF, and LF, which is latent heat of fusion, is going to be equal to Q divided by mass. Q is equal to what? It is equal to 12 subtracted by let's not forget the 10 to the power of 3, so 12 times 10 to the power of 3 minus 1.85 times 10 to the power of 3. Divide this all by what? By 23 times 10 to the power of minus 3. Latent heat of fusion is equal to what? Latent heat of fusion is equal to 4.41 times 10 to the power of 5 joule per kilogram. C, what do we have for C? The specific heat capacity of the solid. Okay, so where is the solid? As you see, this is the solid. This one is the solid. So we have from 0 to 1.85 kilojoule, sorry. Then this is 0 Celsius to what? To 150. So my initial temperature is 0. My final temperature is 150. Let's calculate the specific heat capacity of the solid. So Cp is equal to Q divided by mass times delta T. This is equal to what? This is equal to 1.85. Because we have 0, you can just put it there, but I'm going to write it. 10 to the power of 3 minus 0 times 10 to the power of 3. Divide this by with mass, which is equal to 23 times 10 to the power of minus 3. What is our delta T? It's final minus initial. And it's going to be 150 minus 0. Cp is equal to what? Cp is going to be equal to 5.36 times 10 to the power of 2 joule kilogram per Celsius. We have D. It says the specific heat capacity of the vapor. So what does vapor mean? It means just here we have gas. Here, okay, it's going to be from 855, look, temperature is going to be equal to 300, this is the initial, to 857, so temperature is going to be 450. Now, as usual, Cp is equal to Q divided by mass multiplied by delta T. So Q is going to be 857 times 10 to the power of 3 minus 855 times 10 to the power of 3. You can do something. You can first subtract them and then put them in the equation. Doesn't matter. Or you can just write the numbers in a bracket and then multiply it by 10 to the power of 3. It's the same thing. So 23 times 10 to the power of minus 3 times delta T is going to be what? It is going to be 450, which is T final, minus 300. Okay. Now Cp will be 5.79 times 10 to the power of 3 joule kilogram per Celsius. Okay. We have E. It says the latent heat of vaporization. So remember, what was latent heat of vaporization? It was the energy needed per unit mass to change a substance's phase from from liquid to gas or gas to liquid. Where do we have liquid and gas? And the temperature, as usual, should be constant. So here, temperature is constant and we have liquid and gas. So I'm going to subtract 850 by 55 by 16.6. Now again, latent heat of vaporization, which is the final one. Q is equal to mLV. LV is equal to Q divided by mass. Then I have 855 times 10 to the power of 3 minus 16.6 times 10 to the power of 3. Divide this all by 23 times 10 to the power of minus 3. Then latent heat of vaporization will be equal to what? It's going to be equal to 3.65 times 10 to the power of 7 joule per kilogram. And that's it. We have question 27. A 2.55 times 10 to the power of minus 2 kilogram silver ring. Let me write the givens first. So you have mass of the silver. This is silver. Mass is equal to 2.55 times 10 to the power of minus 2 kilogram. And we have water too. Cp of silver is equal to 234. Then it's heated to a temperature of 84 Celsius. So T initial is equal to 84 Celsius. And then placed in a calorimeter containing 5 times 10 to the power of minus 2. So minus 5 times 10 to the power of minus 2 kilogram. This is water. Temperature is equal to 24 Celsius. Cp of water again is equal to 4,186. And then something important we have here. It says a 0.14 kilojoule of energy is transferred to the surrounding. This is really important. We have to calculate this one too. It says find the final temperature. What is the final temperature? Let's solve this one. It's pretty easy. We have Q lost, which is equal to Q gained. But don't forget that we had 0.14 kilojoule lost to the surrounding. Okay, we have kilojoule, so change it to joule multiplied by 1000. You get 140. Okay, so subtract it to this side. Now Cp of silver times mass of silver times change in the temperature of the silver is equal to Cp of water times mass of the water times delta T of the water minus 140. Let's just write the givens we have. Cp of silver is equal to 234 times mass, which is equal to 2.55 times 10 to the power of minus 2. Then we have delta T. Because heat is lost, it's going to be initial minus final. My T initial is equal to 84. I don't have T final. Then this is equal to 4,186 times mass of the water is equal to 5 times 10 to the power of minus 2. Then times delta T is going to be what? It is going to be final minus initial. Why? Because water is gaining heat. Then T final minus 24, which is T initial for the water, 140. Don't forget this one too. Now, first of all, multiply this and multiply this one too. So we have what? We have 5.967 times 84 minus T final, which is equal to what? 209.2 times, this is 3, T final minus 24 minus 140. Now, just basically multiply them and that's it. Multiply this by this and multiply it by this one. Multiply this by this and multiply by this one. We have 501.2 minus 5.967 T final, which is equal to what? 209.3 T final, 209.3 T final minus 5,023.2, okay, minus 140. These two are both minuses, so this is minus 5,023.2 minus 142, so add them together and the sign should be negative. Let's do this first. So 501.2 minus 5.967 T final is equal to 209.3 T final minus 5,163.2. Okay, this is the result. Now, this is minus, so it's going to be easier to move this one here. T final is minus, so it's going to be easier to move it here. So this is going to be 501.2 plus 5,163.2, which is equal to 209.3 T final plus 5.967 T final. Nothing is remained, just adding them together. So we have 5,663.2 is equal to 215.267 T final. Subtract this by this number. Divide this by this number. Divide the other side too. So 267 cancels. T final is going to be equal to 26.32 Celsius. This is the final temperature of the silver and water mixture. We have question 28. Question 28. When a driver brakes an automobile, friction between the brake discs and the brake pads convert a part of the car's translating energy to internal energy. If a 1,500 kilogram automobile traveling at 32 meters per second comes to halt after the brakes are applied, how much can the temperature rise in each of the 4 3-point kilogram steel brake discs? Assume that the discs are made of iron, Cp is equal to 448 joule kilogram per Celsius, and that all the kinetic energy is distributed in equal parts of the internal energy of the brakes. Now, as you know, we have velocity, so we're going to what? So mass of the automobile is equal to 1,500 kilogram. Velocity is equal to 32 meters per second. We have the mass of the what we call the brakes, but we're going to use that later. Let me write the Cp first, and then let's find what it says. How much can the temperature rise? So delta T is going to be equal to what? First of all, we know that all the kinetic energy is converted to internal energy. Okay, now delta U is going to be 1 over 2 mv squared. Then this is equal to what? 1 over 2, mass is equal to 1000, so this is multiplied by 1000. Let me do this better. So we have 1 over 2 times 1500 times, and then 32 squared. Yeah. Then this is going to be equal to what? Calculate all of this, and you should get 768,000 joules. Okay, this is delta U. Now, before I do anything, I want you to know that delta U is equal to KE, and it is equal to Q. Why is that? Because we have internal energy in heat. Okay, so we have internal energy here as heat, and we have specific heat capacities given too, and it's asking for delta T. We only have one equation we can find delta T with. It's specific heat capacity equation. Now, we can do something. We can first divide it by 4, which is the 4 wheels, 4 brake pads, and then you find the delta T. Or you can just add the 4 later, divided by 4. But let's do this first. Q for each disk, okay, is going to be, or you can write delta U for each disk, doesn't matter, is going to be equal to 768,000 joules divided by 4. So this is going to be equal to 192,000 joules. Okay, this is Q for each one. Careful. Which can be also equal to delta U. So this is equal to delta U2. Now let's find, so Q is equal to delta U, and we know that Q is equal to Cp mass delta T, which is equal to delta U. To find delta T, I'm going to divide this by Cp mass, divide this by Cp mass. So mass, Cp mass cancels. We have delta T, which is equal to delta U divided by Cp times mass. Mass of what this time, guys? First of all, let me explain something else. Here we used the mass of the automobile, which is equal to 1,500, because here we are given the speed of the car. But in the other one here, we're going to use the mass of the pads, okay, with the brake pads. Now, delta U is going to be 192,000 joules divided by Cp, which is equal to 448, times mass, which is equal to, let me see, mass is equal to 3.4, yeah, 3.5. 3.5. And delta T is equal to 122.4 Celsius. Okay. Now we have question 29. A plastic foam container used as a picnic color contains a block of ice at 0 Celsius. If 2.25 times 10 to the power of minus 1 kilogram of ice melts, how much heat passes through the walls? So we have temperature, which is constant, and we know that if at 0 Celsius, if a phase change happens, it says ice melts, there's going to be heat released. This heat, we are calling it latent heat of fusion. So latent heat of fusion for water is equal to 3.33 times 10 to the power of 5. I have mass, which is equal to 2.25 times 10 to the power of minus 1 kilogram. Let's find heat released. Mass multiplied by L sub F, which is equal to 2.25 times 10 to the power of minus 1 times latent heat of fusion, 3.33 times 10 to the power of 5. Then Q is going to be equal to what? 7.49 times 10 to the power of 4 joules. And that's it. Question 30. The largest of the Great Lakes, Lake Superior, contains about 1.2 times 10 to the power of 16 kilogram of water. If the lake had a temperature of 12 Celsius, how much energy would have to be removed to freeze the lake at 0? So we are going from 12 Celsius to 0, and we have mass, which is equal to 1.29 times 10 to the power of 1.20 times 10 to the power of 16. So let's calculate this. First of all, we're going from 12 to 0 Celsius. So Q1 is going to be Cp mass delta T. Cp of what? Of course, Cp of the water. So Q1 is going to be 4,186 times mass, which is equal to 1.2 times 10 to the power of 16, times delta T, which is going to be what? 12 minus 0. Okay, then Q1 is going to be what? Q1 is going to be equal to 6.02 times 10 to the power of 20 joules. That is the first one. Q2 is going to be, because it's a phase change, okay, ice is going to freeze, so it's going to be MLF. Mass 1.2 times 10 to the power of 16 times latent heat of fusion for water, which is equal to 3.33 times 10 to the power of 5. Then Q2 is going to be equal to what? It is going to be equal to 3.996 times 10 to the power of 21. Now Q total is going to be what? Q1 plus Q2. Q total, if you add them together, is going to be equal to 4.59 times 10 to the power of 21 joule. And that's it. This is question 30. Question 30, when it says define a thermodynamic system and its environment. A thermodynamic system, guys, is basically a collection of matter within a confined boundary where there is no matter passing. What about an environment? An environment is anything that can disturb the behavior of the system. And that's it. You basically give the definitions. In what two ways can the internal energy of a system be increased? We can change the internal energy of a system by transferring energy to the system or by doing work on the system. 33. Which of the following expressions have the units that are equivalent to the units of work? So unit of work is equal to joule or Newton per meter. Is mg a unit of joule? No. We don't have any equations. This is equal to weight, by the way. What about this one? It's equal to ke. So yeah, this one is joules, unit of work. This one is, this one is, this one also, this one is not. Okay, so B, C, D, E are, but A and F are not. 34. For each of the following, which thermodynamic quantities have values equal to 0? So an isothermal process, if you remember, isothermal delta T was equal to 0 and delta E was equal to 0 too. An adiabatic process, Q was equal to 0. An isovolumetric process, volume was equal to 0 and work was also equal to 0 too. Can energy be transferred or removed from a substance without causing the temperature of a substance to rise or change its phase? Yes. For example, I can deform an object, okay, without necessarily adding or changing the temperature of the substance. We have question 36. When an ideal gas expands adiabatically, it does work on the surrounding. Describe various of energies that take place. So in adiabatic process, gas is going to expand very rapidly, and the gas is going to use the internal energy of the system to do work on the surrounding. You have question 37. In each of the following cases, trace the energy transfers as well as changing internal energy. First of all, we have A. So when you are rubbing your hands together to warm them on a cold day, you are basically doing work on your hands by means of friction. The internal energy of your hands is going to increase and your hands are going to feel warmer, okay? Of course, you're going to do work on the surrounding air too. Some of the heat from your hand is going to be transferred to the surrounding too. B, if you have a drill, okay, made of course of metal, when you add a small amount of water in the place of the drilled hole, steam rises from the hole. So basically, when you are using the drill, you're going to increase the internal energy of the system because it's having a friction with the wall or with the drilled wall. This internal energy is going to be transferred to the water and rise the temperature of the water, and then steam rises from the hole. We have question 38. Paint from an aerosol can is sprayed continuously for 30 Celsius. The can was initially at room temperature, but it feels cold to the touch. What type of thermodynamic process is it? For a small sample of gas, it leaves the high pressure. So it's high pressure to the gas is rapidly going out from the can. So this is going to be out from the container. Sorry. So this is going to be an adiabatic process. 39. The can of spray paint in item 38 is set aside for an hour. During this time, the contents of the can return to room temperature. Why? What type of thermodynamic process is this? The process is isovolumetric because the gas returns to room temperature without any change in the temperature. Sorry, in the volume. What we call the paint is cooling down without any temperature, any volume change. So isovolumetric. 38 is adiabatic. 39 is isovolumetric because no volume is changing. This is it for this video. I'm going to finish the rest of the questions in the next video. See you in the next video.